Yeah, it's working, but it doesn't show the timing. Yeah, now it's Can you speak, sir?
Hello, hello, hello.
Yeah.
Okay. So, so if you recall correctly, our numbers are like x1, x2, or whatever you want to call it, x1, x2, xm, which are element of 1 to n, and and we defined fi is number of times, say, xi occurs. Okay. So this is the frequency of I. So Fi is basically frequency of I in the stream. Okay, and as I told you before, like, so what is our goal? So now suppose, so Fn, this is what you are going to get, right? So at the end of the stream, you will have some vectors of this nature, which is basically tell you how many times x1 occurs, how many times x2 has occurred, and everything. And I told you that every move or every update is of the form uh, I comma delta. Okay. So I am focusing just myself to say up to 1 to n, but we'll see later that how we can make it to Rn and everything. On purpose, I have just kept it to n. Okay, just to change and have a slightly change in perspective of what we wanted to compute. Okay. So the reason why I wanted to do this is that I thought that first I will teach you from the linear sketching perspective, but I thought maybe the best thing is for now is to take a perspective. What we have been doing all the time is to compute, come up with unbiased estimator, do repetition, and do median. Okay, and finally we'll see how we can put all these things, whatever we are doing now, in terms of linear sketching. Okay, so forget it. I mean, just think that these numbers. I know these m things are coming in the stream. This, and given f1 to fn, my objective is to compute some function g, okay, of say suppose this is some stream. So what is g of rho? So g is some function, okay. G is a real valued function, okay. So g is a real valued function, and what is 0 is summation I in 1 to n g of fi, okay, and z0 is 0, okay. Notice that if g of x equal to x power k is nothing but the kth moment, right. So if I take g of x as x to the power k, then this is the kth moment, right, because what is g of fi will be fi to the power k, and that is what we are trying to compute, okay. And so there is another example of g which is used quite a lot, is what is called x log x, and where x is fi by m, okay. So this is basically computes entropy function, okay. So this is entropy function. So these are the two things which has been used quite a lot, okay. Okay. So what we are trying to do first is trying to come up with an unbiased estimator in this setting, okay. So what is this setting? So we are given these x1 to xm, where each xi is a token or number from 1 to n, and let fi be the number of times xi occurs, which is basically the frequency of xi in the stream. So there's like it's just insertion only stream, don't worry. Huh? Frequency of I in the stream. Yeah. Yes. And I have defined the function g rho, which is a real valued function with an additional property that g of 0 is equal to 0. Okay, so I'm now trying to construct an unbiased estimator for this, right? And then we'll try to use this to obtain what do you call a streaming algorithm from with the help of this estimator, and then we will do usual Chernow variance and all those kind of things. So how do you think we are going to get an unbiased estimator for this? So this is the whole trick of AMSs. This unbiased estimator was given by AMS. Okay, Alon. I don't know what is this person name. Now I forgot. Matthias, and S is for, huh? Okay. I don't think I can. Z E E G E D Y. Okay. Okay. So hint. So and this is the reason why I chose this presentation, because it's, at least to me, it's a bit more natural than doing an unnatural thing, and then we'll get to unnatural things. Okay. Okay. So what do you know? Okay. Imagine yourself that, forget about what do I know? I don't even know how many items are going to come, but I know how to sample uniformly at random. I don't know how many items are coming, but I know how to do a sample uniformly at random an item, right? This is what we learned reservoir sampling, right? So suppose I want to use that, and with the help of that, I would like to make an unbiased estimator. How do I go about it? Okay. So let J be uniformly at random sample from 2. We know how to do this, but suppose, forget it, we are not even worried about how do we implement it. We are just trying to get a random variable, set up a random variable whose expectation is exactly what I want, right? This is all that I want. So suppose J is uniformly at random sample from my data stream. Okay, so this is in your hand. Can you use this object to create an unbiased estimator? Okay, so sample. So J is uniformly at random in 1 to m. Okay, so given this, I want to create, so J is equal to some xi, okay, which is equal to, say, some little j, right, between 1 to n. Okay. What can you, so what could be, what is the frequency of j? Is like fj. Okay. So suppose I selected, so uniformly at random you got j, then what is the probability that how to say this? Okay, what is the probability how do I say that? Okay, let me. So let me define R. So these are basically so what I'm going to do is R is some J index, okay, and this index is greater than equal to J, less than equal to M, and what is the property? Xj is equal to Xj, right? So what is this? What is this set R is? All those indices where my current item occurs, right? This is exactly. So suppose uniformly at random, here is my sample, okay, and I picked up an object here. So this is what I picked up, xi, right? Here, this is what, I mean, I shouldn't say, this is what we have picked up. So xj is in 1 to n. So this is at the jth coordinate. Now, what are these little j's? All those places where this element occurs, right? This is the set R is, okay. So what are the possible values of R? So R is a random variable. Notice R is a random variable, right? So cardinality of R. So what I'm more interested in is, say R is this. I'm more interested in cardinality of R. Okay. So what are possible values of R are? What? What are possible values of R is? What? 1 to m minus? No. Look, J itself was uniformly at random in 1 to m. So that's a random variable. Okay. And even if that is true, this is not what it is. Even if you think J is fixed, it is not what you think. Can you give me an upper bound on R? What? Again, R is a random variable. Okay, so suppose this number is xj, it's some I. Okay, what are this number? What is the value of this guy? What is the value of this guy? What is the value of this guy? So if xj is going to be equal to I, it can be one of these guys. And what is this? It's a frequency. So the cardinality of R is bounded by f of j. I mean, what? Xj. These are indices. Frequency of xj. Okay. So it's not anything, right? So if I picked up the first guy, then it is equal to frequency. If I picked up the second guy, it is frequency minus 1. If I picked up third guy, it is frequency minus 3. If I picked up the last guy, it is 1. So it varies from 1 to the frequency, right? Because this is exactly what is j index of j between j and m, where xj is equal to little xj is equal to xj. So it is precisely those values where I am equal to this. So it is not m minus j and this and that, but it is actually bounded by how many items appear, how many items of my value appears after me, right. So claim, let's see, okay. This random variable is uniformly at random in this. Given that, I mean, so given that we are going to pick up say xj, whatever that xj is, say this is I, okay. So given once you fix that you are going to get I, condition on the fact that you are going to, whatever the number you are going to get is I, right, then it is uniformly at random over 1 to fxj. Right, because what is the probability that I am going to get third? It is a probability that I am going to get frequency to be third is that I am going to choose this particular entry, and that is with 1 over m. What is the frequency, what is that I am going to get this, so I have to choose from, so it is like 1 over f of xj. What is the probability that I am going to get this number? Well, I have already fixed I, so there are only these positions which I am considering here, right. So having fixed I can get any of these position uniformly at random, and if I get any of this position uniformly at random, that will imply that cardinality of R is uniformly at random among these numbers, okay. Okay. So once you fix an element uniformly at random, there is another random variable which depends on this, which becomes uniformly at random on its frequency, okay. So now how do we are going to use this, okay. So having said this, our unbiased estimator is very simple, is y m times okay. So for where this m is the total number of items. Okay. So let us prove this lemma, let us prove that it is indeed an unbiased estimator. So what you have to show, that expectation of y is equal to 0, right, which is equal to summation I in 1 to n g of f of I. This is what I have to show. Then I am done that, then I have a very good estimator, right. Then it is an unbiased estimator for the object which we are interested in, right. Expectation of y is exactly what I want, okay. So y could take any of these values, okay. So what I am going to write is that I am going to take, look, depending on what xj is going to be, okay, I am going to define my okay. So summation I going from 1 to n, probability that say xj equal to I, okay. What is an expectation of y given that xj equal to I, and I am summing over I equal to 1 to n, so this is perfectly fine. What is the probability that xj equal to I? Divided by m, because it is uniformly at random, j is uniformly at random in 1 to m. So what is the probability that xj equal to I? Number of times I occurs divided by m. So which is frequency by moment. So summation I going from 1 to n Fi divided by m. Okay. Now what is now I would like to compute this quantity, right? This quantity is going to be something minus something depending on what is the value like of this guy is, like whether it is this I or 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 it is this I, depending on which I we are going to pick, right? This value is going to change, right? So this value depends on which of the ith object you have picked uniformly at random. So this quantity, this expectation is what function it can take and what value it can take and its probability. Am I right? So this is going to be summation. Okay, so it is going to take m times. So let's call this L equal to 1 to Fi. This is the possible values it can take, right? Right? So these are the possible places where I could occur, like, okay. But if I occur like which place I occur, this quantity will change, right? So this is going to be G of L minus G of L minus 1 probability that what is that called? Probability that not y. What is the probability that that's so just 1 by Fi. So how do I say this? I mean probability that xj equal to I and xj equal to I and xj equal to Lth I. Lth I. Okay, and this we know is just 1 over Fi. Okay, so summation I going from 1 to n Fi by m summation m over Fi G of L minus 1. Okay, so if I take this out, m and Fi will get cancelled. What I am going to get then? What I am going to get from here, right? G0 and G of Fi, but I assumed that G of 0 is equal to 0, right? So this is going to be equal to G of Fi. Okay. So we are still in this setting of insertion only model and like things, but do you agree this is an unbiased estimator for the object we are interested in, right? And there are many G's who satisfy this property. Okay, so this was a note in AMS paper, so I thought, okay, let's play with it. So they do it for just moment estimates, and there is in conclusion there is a written that for any G which has this property, like the estimator works, right? Whether variance will work or not, it depends from this thing, and they had given example of these two. Okay, but that's it. Yeah, and you just follow the proof. It's like it's really just works. You just replace the right word with right word. Okay, okay. So what we have achieved now? We have achieved an estimator, okay, unbiased estimator for our object. Second is, how are we going to compute the value of this estimator in small space, right? Okay. So now next is I'm going to tell you how to compute this y, because this is what I would like to output, right? Expected value of y is what I would like to output, right? Now how do we going to, what all things do we need so that we can output y in small space? So algorithm is clear, right? This is what, like, if I would have been doing a deterministic algorithm, right? If I would not have worried about what do you call? If I would not have worried about, suppose these strings were coming and I wanted to do something, I mean, I would have just uniformly random picked this, and I would have computed this number after that, and then outputted this, right? And I would have been good with very, I mean, we'll worry about how good or how bad, but suppose this is what I would like to output. So how do we go, how are we going to maintain this y in small space, okay? So the next question is, and then we'll worry about what is its quality, what is its variance, and this and that, but at this point of time, our job is just an algorithm where these things are coming in a stream, and I would like to output y. So to output y, I need cardinality of R, I need this to be uniformly random, so I need these two things, because once I have these two things, I can compute this function and give it to you. Okay, so let's try to do it. Okay. This, I mean, this is just a puzzle. It's not, I mean, I'm not going to use any. And something should tell you that, look, I'm only interested in, once I have decided that this is an element which I want, what do I want after that? I only want to know how many indexes are there where I am equal after me. Right? So it is not, it does not depends on what has gone ahead, it only depends on what is going to come, right? And that I can do, right? Okay, so let's see how we maintain this, okay? I never said it is difficult.
The question is, what are we going to do now? I mean, it seems like that.
Yeah. So reserve is something you can do the uniformly.
And then
That you count R.
Yeah. Whenever you
how?
you sample.
You know what variable you have seen, so you just have to look for it.
But you might replace it. Reservoir sampling replaces, like, I'm storing something as my current uniformly at random object, right? With some probability I keep, with some probability I don't keep it. So I just have to handle these two cases. Right? Right? How did we do? So when say, look, I'm coming, ith item is coming, I keep the new guy as my uniformly at random sample object with probability 1 over I. Right? So now that I have kept, so my R also changes, right? But that's it. I mean, this is nothing funky. Okay. And I also just wanted to see that how reservoir sampling is used, like as a subroutine several places. Okay. So this is called AMS estimate. Okay. While stream is not done, what should I do? First thing, I increase my M, like number of items. Okay, great. Suppose XM is the current item. What does reservoir sampling should do at this point of time? We toss a bias coin, that is head with some probability and tail with something. Okay. Toss a biased coin that is head with probability 1 over m. Okay. Okay. If coin turns up head, what do we do? So suppose S is that uniformly at random object which I want to stir. So what should I do now? I should replace, right? So I should make a xm as my new sample. Okay. Then what should R be then? R is set to 1, because now I have changed my uniformly at random object. So this is my current object with which I am going to compute my R. That's it. And else, what will you do? So suppose I did not replace, then what should I do? I should check if xm is equal to the sample, I should just increase r to r plus 1, that is it. And while, okay, and what should I output now? I have m, suppose I have g, so I should just output this object, right. So I will output m into g of r minus 1, that is it.
Existing numbers, so we don't need cardinality of R here.
R I wrote set,
But here you are increasing S.
yeah, so right, correct, sorry, yeah, okay, so this is, okay, simple, done. Now what is its quality? How much space first of all it takes? S is some number between 1 to n. So how much bits of space this is going to take? Log n bits, right. M is some number between 1 to m, right, like m, right, is a number of items which is log m bits, like total number of items is going to come. And what is R? It's a frequency. So frequency cannot be more than m, right. So this also will take at most log m bits, and then whatever the computation time takes for this, suppose this is cheap for now, then this algorithm takes order log m plus log n bits of space. So space wise this is a very good algorithm, but quality wise we still do not know how good or bad it is, okay. 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 So now I am going to apply, I am going to check this quality by for k greater than equal to 1, okay. I mean for different ranges we will see different, like we will see various avatars of this algorithm in the coming, but this is the most easiest of them, and it had already achieves very good qualities or very good properties. Okay. So expectation is great, but I don't like till you don't know, tell me the function properly, I cannot compute its variance, okay. So we will only do it for, I mean like we will fix kth moment and we will do it for that, okay. So I want to estimate fk, the kth moment for k greater than equal to 1, not even 0 or something, it is important that we use k greater than equal to 1. So basically I am going to do for function x power k, okay. So here is a lemma which I would like to prove, and let us see if I can prove this, why we are in good shape, okay. When gx is x power k and k greater than equal to 1, then variance of y, and remember this is what your y was, okay. Variance of y is less than equal to k times fk, no, k times f1 f2k minus 1, which is less than equal to k n minus 1k fk square. So this is what our variance will be. Suppose we prove this, okay. Suppose we proved that our variance of y is going to be this quantity, okay. Then if I would like to apply, Chebyshov. What should I do?
What is capital A?
So let's,
What is capital A?
capital F, kth moment for k greater than or equal to 1. So summation fi to the power k, little fi to the power k. So fk is summation fi to the power k, right? Yeah. Is that what it is? No? Yeah. How many times, look, and this is summation over I going from 1 to n, right? Look, I told you, right, we are in a very simplistic setting where each xi is from numbered from 1 to n, right? So how many times that number has occurred to the power k? Where fi is the frequency of I. Okay. I mean, we will see also over reals and these things, but for now let's just stick to this. So suppose if I would have shown this, then what is a probability that so now if I would like to apply Chebyshov, okay, so what is this? Y minus expectation of y, right, is, what can we say? Right, is greater than or equal to sum A is less than or equal to variance by A square, right. So what is our variance here? So we know what expectation of y is. What is expectation of y is going to be in this setting is going to be summation fi to the power k. This is what expectation of y is, okay. So what will be this? If I just apply directly to this, this is going to be less than or equal to, what is my variance of x is going to be this k times n 1 minus 1 by k fk square, right, by a square, okay. I do not want this to deviate too much from its expectation, right. I do not want this to deviate too much from its expectation, right. So do you really think I can write, if I want this to be less than or equal to some half, right. So what should be a square be? So look, a is for sure, what is a square is like fk square, right. Whatever it is, whatever a I will write, say suppose I write a equal to some delta times or some say c times, right, expectation of y, which is c times fk, then this is going to be c square fk square. So this and this is going to be get cancelled, but c is going to be very, very bad number. C is going to be very, very bad number from here. So what trick did we do to reduce variance? To reduce variance, what we did is we did lot of things in parallel, okay, and we took the average estimator, right. So what we did, so to do this, the trick which we have been doing is repetition and average. Okay. So suppose I now have y1, y2, y some number of times, okay. YH will fix how many independent copies we are going to do this, and what is y prime is basically summation yi divided by h, but these are independent estimator, right? And if I fix h, so look, I want to fix h as some number of times and some expectation so that these guys get cancel each other, okay. So what should I take h to be equal to? Suppose I take h to be equal to c by epsilon square k times n 1 minus 1 by k, okay. So what is now what is the variance of y prime? Variance of y prime is going to be variance of y divided by h, right. This is what we saw, like we have been seeing this. So what this will be then, if I take so much copies, then this is going to be less than equal to variance of y is this. So this is going to be equal to fk divided by fk square, right, times epsilon square by c. This is what we are going to get from here. So now if I apply this, what will be probability that y prime minus expectation of y prime is greater than equal to c times expectation of y prime is less than equal to, by Chebyshov this is going to be equal to variance of y prime divided by c times expectation of y prime whole square. No, let's put epsilon, because this is what we want, okay. So now what is this going to be equal to? This is going to be equal to whatever this number we are going to get, okay. And look, what is expectation of y prime? Expectation of y prime is same as expectation of y, because it is an independent copies and you are doing sum by h. So h into h will get cancelled and you are going to get the same thing. So now if you do computation, this should come out to be 1 over c, okay. So I am not going to the details, but this is what you are going to get. Now this is amazing, right, because c is in my hand, right. So what did we do? So if I wanted this probability to be less than equal to some delta, then it will be like some proportional to fk square epsilon square c. I choose c appropriately like delta, right. So number of copies which we will be running is like c over epsilon square delta times this, right. So if I wanted this to be less than equal to delta, right, so I am not too much away from epsilon with success rate delta, then if I want it, then the number of times my h has to be computed is c over epsilon square k times n 1 minus 1 by k times 1 over delta, right. So I can achieve what we call epsilon delta success in these many repetition, okay. But we also know how to reduce the dependence on delta. How? We apply this algorithm with epsilon equal to delta equal to 1/3, okay. So c equal to, so let's apply this with 1/3 and then we do the median trick, right. So if I do this median trick, right, what I mean by this? So I will call this algorithm bunch of times and then take the median of that, right. And if I take the median, now if you apply median trick on this, okay, we will get the dependence H new dependence will be C over epsilon square log 1 over delta times K n 1 minus 1 over K, right? Okay. So if this is what it is going to be, so how much space it is going to take? So the space is going to be this time log m plus log n bits, right? Okay. So for in general, this is more or less equal. So this is not the best bound because the best bound has 1 minus 2 by k, not 1 by k, but this comes very close to the best bounds. Like the best, like a space bound will going to be 1 minus 2 by k times this, like in general for any k greater than equal to 1. So this computation was for any k greater than equal to 1, and I told you last time, if you remember, that for k strictly more than 2, this is the best we can hope for, right? For less than equal to k equal to 2, we will do something different and we will, okay. So all I need to show at this point of time, so this is usual trick. So what we did, we came up with an unbiased estimator, we implemented that in the streaming setting, okay. Then we computed its variance. To reduce its variance, we repeated it several times and we took the average, and to reduce the further dependence to get it to log 1 over delta, we first computed this approximate solution with 1 by 3 success probability, and then I repeated that algorithm bunch of times and took medians to get log 1 over delta, okay. So all it depends on how do we go and compute this variance, okay. So I just wanted to show you more, like almost all the algorithms more or less follow this template, and when I'm going to do linear sketching, I'm going to do this, many of these steps just in one bunch, and that's it, okay. So that was my whole purpose to show you this example. So what I'm left with is to show you this lemma that variance is this, and once I show this, I will be done, okay. Okay, questions? Because after this we are going to do some mindless maths. Like idea wise, that was an idea and rest is just an implementation, okay. But why should you believe me? Okay. Okay, so let's do this computation. Okay, and for this we are going to use the fact that this function is convex. We'll use that crucially. Okay. So okay. So what is variance of y? If you recall correctly, it is expectation of y square minus expectation of y whole square. This is some positive quantity, so I will just show you this. I ignored this, right? So I'm going to show that variance of y is less than or equal to expectation of y square. I'm going to give an upper bound on this in terms of these two, okay? So I'm only interested in expectation of y square, okay? Okay, so let's compute expectation of, so now I'm going to write you variance of y is less than or equal to expectation of y square, and now we are going to do exactly what we did before. Probability that xj equal to I in 1 to n, and summation, okay. Now it is this function, right? So it is going to be m square by fi square, because with probability 1 over fi we are going to do this, right? We are going to succeed this, so fi square, and what will be this? Some L going from 1 to fi L power k minus L minus 1 to the power k whole square. This minus this to the power whole square. These are the quantities which we are going to get, right? Because we are only in the regime x power k. So this is the function, and its a square is the value what this random variable y square is going to take. So this is what the y square is going to take, okay? No, what I am writing, this is not correct. So this is a value which is going to take with probability 1 over fi, not 1 over fi square. I mean, it is going to take the same value with the same like square of this value with the same probability, right? So all we have to do is to do a mindless computation on this, okay. So this is equal to summation I going from 1 to n, this we know what it is. What is this? This is going to be fi by m summation L equal to 1 to fi m square by fi Lk L minus 1 to the power k whole square. Okay. So for a change, I am going to write this Lk, right? It's just squared, so I just wrote it twice. Now what all things will get cancelled from here? Notice fi and fi will get cancelled, m and m will get cancelled, and this m is uniform over everybody. So I can write down this as m, I can pull it out common, summation I equal to 1 to n, right? And summation L equal to 1 to fi, let us see if I can replace some things with some things, okay. Okay, so I am going to write this term as k times Lk, okay, minus 1, okay, and this is funky, k times Lk minus 1 times Lk minus L minus 1 to the power k. Why did we write this? Because here is an inequality which is true for greater than or equal to 1, that xk minus x minus 1 to the power k is less than or equal to k times xk minus 1. Please prove for yourself, I am not going to do this. I verified, it worked. You can do calculus, differentiation, whatever, right? You can replace this with this, okay? Please forgive me for not doing this, okay? Okay, excellent. So what all things now I can take common, okay? Let's see, okay? See, I'm doing some mindless computation, so I mean you have to give it to me for first of all doing this for you, okay. I want to say that, so notice that this k also I can pull it out. So now I can write down km summation I going from 1 to n, okay. Okay. So now I want to write something slightly differently, okay. So let us try to see this term, okay. Let us try to write it down, this term. So what is these terms are? So I will start with fi on purpose, okay. So let us write it down. This is going to be L is going to be fi to the power k minus 1, fi to the power k, and what is this? Fi minus 1 to the power k. So this is the last term. What is the next term? Let us try to understand. The next term is fi minus 1 k minus 1, fi minus 1 to the power k minus fi minus 2 power k, so on and so forth. I would like to no, this is plus, okay, this is plus, right. I would like to take this term and this term and club together, okay. So what happens then? So let us look at these two, this term and this term. So this is going to be fi k minus 1, fi k minus 1, right, fi k minus 1, fi minus 1 k minus 1, and then I am going to I am going to take this term and like look at these two. So this is minus and then this is plus fi minus 1 to the power k minus 1, fi minus 1 to the power k. What can you say about these two terms? This term is going to be negative. This is a negative quantity. Why? Because this is common term, and this is fi k minus 1, and this is fi minus 1 to the power k minus 1, right? Do you see this? This is a negative quantity. Okay, why? Because let's take fi minus 1 k minus 1 common. Then what are you going to get? You are going to get fi minus 1 to the power k minus 1 minus fi to the power k minus 1. This quantity is only going to be smaller than this quantity, no? Because they have the same power and this is a smaller number. What?
Fi minus 1 raised to k.
Fi minus 1 raised to k inside the bracket.
In the first sum.
What is this?
The first term contains fi minus 1.
To the power k. Okay, and what does the second term contains? Is it second is correct? So this is also fine, right? Because I was only taking this common, okay? So this is fine. So this is still negative term. So what do we get from this? All this is that this is the only term which dominates. Rest are negative. So if I am interested in upper bound, I can write it down fi k minus 1 fi k. That's it. Because you can group these two terms together and all these are negative terms, so they all only contribute negatively. So if I am only interested in upper bound, I can use this as my term. Okay, excellent. Okay, my God. Okay. What is this? What is this? So have we achieved the first term, right? This is less than equal to k times m times f 2k minus 1. What will be f1? Is equal to m. f1 is going to be equal to m, right? Just sum them. So this is why it is equal to k times f1 times f 2k minus 1. Okay, so at least we have shown this. Now I will show you that this quantity is less than this quantity. And this is where we will use the fact that this is a convex function. I mean, it's not fun doing all this. It's like, okay, fine. Okay, so now, anyway, we have this term k, so let's forget it. We'll focus on these two terms. What is this equal to? What is f1 is equal to summation fi, this is what it is, and this is equal to summation fi 2k minus 1, okay? Okay, so let's call f infinity is equal to max I fi. So f infinity is max of all these f frequencies, okay? So here we can write down this as summation fi, and now look, it is fi 2k minus 1, right? So I can replace this with f infinity for whatever quantity I want. So I can write it down, this is nothing but f infinity k minus 1 summation fi k. I replaced every f1 to the power k minus 1 with f infinity to the power k minus 1, and then I took it out, because f infinity is max of each of these quantities. So this is perfectly fine. I am only using upper bound, okay? But now comes the funny part, okay? So now I would like to replace this f infinity to the power k. Look, I think you do all this mindless maths but okay, what I have to show? I want to show f infinity k minus 1 is less than equal to summation fi to the power k minus 1 to the power k. This is what I would like to show. Do you believe this? No? You don't believe this? Okay. So let's just take inverse power, like, okay. So what will I get here? I will get f infinity k minus 1 to the power k by k minus 1. Agreed? Okay. So this goes. So what is this? F infinity to the power k. Man, f infinity is one of fi, right? That occurs here also, right? So that's it. So I can replace this with this, because do you get my point? What is f infinity to the power k? It is one term here, right? I am summing up more numbers here, right? Because f infinity is max of fi. So somewhere this max is going to occur here, right? So this is fine, okay. Okay. So this is less than equal to summation, let's say I not, suppose f infinity is equal to some f j, it could be I not equal to j fi to the power k plus f infinity to the power k. This is what it is, right? So we can use this terminology here, okay. So now, okay, I'm going to rub this because we are done with estimates and everything. Okay. So that quantity is, so what is this? Fi summation fi times, what did I write there? Summation fi k to the power k minus 1 by k, right? Right? And then we had summation fi to the power k. So of course we can add this up, no? So what are we going to get from here? Okay, but let's not add them up yet. Okay, this is what it is. Okay, and this is an inequality which will prove, or you will prove. So here's a claim. I'm not going to prove this. Okay, this is not very hard. At least I checked. 1 to n xi by n is less than equal to summation I equal to 1 to n this is where you will use convexity, and we have proved this several times in our probability course. Okay, so this is the inequality which I would like to use. Okay, so please, so the guy who is writing this should prove this. Prove using convexity. Okay, if I start doing all this, then we will never see the nice things. Okay. So now I would like to use this in this estimate. So how will I going to use this? Where will I use this? You see here, k minus 1 by k? So I could use there, no? So first one, okay. So what should be the first one then if I do this? So what will I get for the first one? So this quantity is going to be equal to n to the power 1 minus 1 by k, because n will go here and n to the power 1 by k will come from here. So I will get n to the power 1 minus 1 by k and this quantity, right? Summation I equal to 1 to right. So this is what I have replaced this with, and then I have all this quantity. I think we are very close to whatever we want. Okay, but what is this quantity? This is exactly what fk is, right? So this is n to the power 1 minus k, fk, what is this? 1. Oh, sorry, this is 1 over k, right? So this is 1 over k plus 1 minus 1 by k plus 1, right? Each of them are the same object, right? So what do we get? N to the power 1 minus 1 by k fk square. Okay, question. Okay, so now we will focus on F2. Question, any question up until now? No. Okay, so what did we learn? We learned that we can do estimates on, okay. So what we learned that we can do estimates for fk in space O tilde n to the power 1 minus 1 by k. Of course, there is some epsilon delta hidden here, right? But this is what we can do. Okay. Now what I am interested in is F2, and I want to so now I am just interested in F2 estimate. So what should be my first goal? Come up with what? Unbiased random variable, right? So we need an unbiased random variable. Okay. As always, I don't think we need this. Okay, so let's see what happens if we say these guys are coming in R for now. Okay. So what I do at every time, I toss a coin. Okay. Toss a coin. Okay. And if head comes, I take -1. Tail comes -1 with probability half. So this is +1. And my y is, so suppose at Ri is your random variable at the ith instance. So this is what you are going to do to m Ri xi. What you can expect, and I am going to output y square. So this is my random variable. Y square is my random variable. What is expectation of y square? This is a fairly simple algorithm, right? For now, let's just say they are in 1 to n. I don't know whether it will matter. We'll see. Okay. Otherwise, we might. So it's just still insertion only string. What is an expectation of y square? So expectation of y square is going to be okay. So let's maybe this is not the right way. I don't think, no, I think I'm not doing something correctly. Okay. So I know they are from 1 to n. Okay. So Rib -1 to the power n. So where uniformly at random. Okay. So Ri is, so some vector R is this, which is basically you are getting +1 -1 +1 -1 blah blah n times, right. So this is, which is basically at each, for each element index 1 to n, I am going to compute like going to toss a coin. If it comes head, I put +1. If it comes right head, I put +1. Tail, I put -1. Okay, and I am going to output Ri Fi. So this is my random variable. Okay, y. So now let's compute what is the expectation of y square is. So what are the possible values y square could take? Hmm? So what is the probability that Ri square, so what are the possible values Ri square will take? Ri square is going to always take plus 1 with probability half or 1. 1. So Ri square is just going to be 1, is going to equal to be 1 with probability 1. Okay. So now okay, so let's do it. So maybe let's use them as not Ri, but maybe use them y1, y2, yn. These are my random variable, yi, fi. So what is an expectation of yi? What is an expectation of yi? Huh? What is expectation of yi? Is 0, like 1 with half, so this is 0. Okay. And what is an expectation of yi square? Is 1, because it takes 1 minus 1. Okay. What is an expectation of yi, yj? I not equal to j is 0. Why?
There was independent. So
Yes, they are independent. So this is expectation of yi times expectation of yj, which is equal to 0 if I is not equal to j. Very good. And if what is expectation of yi, yj if I equal to j? Very good. So now we are interested in computing this. So what is an expectation of y square? Is going to be summation expectation of this function, summation I equal to 1 to n yi fi whole square. Now notice that by linearity of expectation, any yi, yj, look, see if I write down the whole square of this and then take linearity of expectation, any term which has yi, yj, because these are constants, right? So any term which has yi, yj where I is not equal to j is going to get cancelled out each other. So this is going to be equal to summation over ij expectation of yi, yj, fi, fj. This is what it is going to be equal to be, right? And maybe there are some constant and this, but since I not equal to j, this term is going to get cancelled. So then we are going to get I equal to j, right? So or we are going to get summation expectation of yi square fi square, which is same as summation fi square expectation of yi square, which is 1. So what did we get? Fi square. Okay, so this is amazing, right? Okay. How are we going to implement this in a small space? For now, if I did not worry, I did all the computation which I did in the board, right? And I just want to, look, I'm not worried about implementing this in, what do you call, I'm not worried about variance, this, there's nothing. Just as an algorithm, how are we going to implement this? Look, if I am going to demand this n-bit vector, I am dead. So I have to be clever. So look, this was fully independent random variable, but please look at the computation. Look, I just chose this uniformly at random, right? I chose this R where each bit was plus or minus 1 with probability half. I chose this uniformly at random. But in your computation, what did you use? just 2 wise independence, because all we needed is that expectation of yi yj is expectation of yi times yj. So if I am going to sample this R from 2 wise independent random variable, I can prove the same. So what should be my algorithm? My algorithm is this beautiful algorithm. Okay. I will not tell you that, I mean, we might need more power of universal, like more wise universal hash function, because we also have to control variance, but we'll worry about that later. So what will be an algorithm now that we have? So what, we have decoded our estimator. We know that estimator requires a n size random bits, where this n size random bits is nothing but 2 wise independent random variable, and for 2 wise independent random variable, how many bits, what all things do we need? 2 numbers, A0, A1, right? So okay, so let H be 2 wise independent hash family from, by the way, do you know how to construct this? How do you get 1 minus 1? Forget about this, how do you get 1 0? Look, 2 wise independent random, I told you how to get this function from this field to that field and all, right? This polynomial. Generally when you have to reduce a domain, you just look at the amount of significant bits from the last which you need. So 0 or 1 is going to be with uniformly at random probability. So you treat 0 as minus 1, and this is how you take a projection on the last set of bits and you reduce the range from anything to anything. So this is one trick. We'll do more, but suppose we can compute this for now. So what we'll do, pick H from H uniformly at random. So this is what we did. Okay. Okay. So what will we do? So initially Z is 0, while stream is not empty. What will we do? What should we do? And suppose Xj is a current item. What should we do? What should be the Z? What should be the Z? Of course, Z should be Z plus H of, yeah. Output Z square. That's it. How much space it will take? Log n space, okay? But we will show that its variance okay, we need to compute its variance also, right? We have to also show its quality, right? And we will say that its quality is quite good, so we don't have to repeat it like n to the power 1 minus 1 by k times, but rather some polylog n times will be sufficient. But for that we will not need 2 wise independence, but since we are going to compute variance, there will be 4 terms which we like to cancel out each other. So rather than picking from 2 wise independent random variable, we'll pick it from 4 wise independent random variable, okay, and then we will be done. Okay, so this is the precursor for tomorrow. Okay, Okay, so what we'll do tomorrow is take up this algorithm for F2 estimation and just F2 estimation and do these things, and then we will look at other ends and how these things are. So probably we will spend another week on moments. Okay, yes. Please figure it out. Otherwise, I will anyway tell you tomorrow, but so maybe you have a day to think about it.
yi is the fi is what? Frequency y. So you've got one more exchange.
Yes,
So you just have to manage one.
yes,
You've already done your previous fi.
yes. So, okay, so let's take a break here and we will tomorrow see F2 estimations.